I give a small introduction of you before we start.
Okay.
So welcome everyone. It's a great pleasure to introduce Dr. Cédric Lorcé from Palazzo. So Cédric did his PhD from University of Liège in 2007. And after that, I think he went to do 2 postdoc in University of Mainz as well as in University of Paris Sud. After that, he joined Center de Physique Theory, CPHT, and of the École polytechnique. And I don't know which year, Cédric, but maybe last few years.
2015. So
2015, yeah, 2015, and from then Cédric is in CPHT. So he works in different topics. He's primarily working on particle physics and working on several other directions like spins, symmetries, and higher spins, solitons, instantons. So today, Cédric will talk about relativistic charge distribution. So again, thank you, Cédric, for accepting our invitation and to give this talk. You can start now.
Okay, thank you very much. And thank you all for being around. Yeah, so as it was given by Ms. Rue in the introduction, I'm working in the field of hadronic physics. So we are interested in understanding the structure of, for example, the nucleons, protons, neutrons, in terms of the fundamental constituents, and we have different tools to do so. And I will be discussing recent developments for one typical kind of object that are interesting to describe a system is essentially the charge distribution of those systems. So this has already a long, old history, back to the 60s, basically. But then new things appear about 20 years ago, and we'll discuss it a little bit here. And now with the new picture that can basically interpolate between the two things. So I know that not all of you are working in the field of particle physics. They are not necessarily working with relativity. So I try just to show the main physical ideas and making connection with other fields, because it's not totally disconnected. So if you have also questions, don't hesitate to interrupt me, of course. So this is basically the program I wanted to discuss today. So basically we start with words about the elastic scattering and physical information we can get from this kind of experiments, and especially come to the notions of charge distribution, so it shouldn't be an S here, in different Lorentz frames, so different observer frames. And we see that in the relativistic case, the frame dependence is important. And to understand that in a more generic context, I will present the new things that I've recently proposed and developed, essentially using a phase space picture that originally came from ordinary quantum mechanics, non-relativistic quantum mechanics, and have the generalization in a generic frame. So we start just with the picture we have about the structure of the proton. So basically, when you look at the spectroscopy of hadrons, and for several decades, people noticed that essentially most of the hadrons, almost all the hadrons, can be described in terms of finite small number of constituents that we call constituent quarks. And basically the mass of the system would just be the sum of the mass of the constituent with a little bit of binding energy, just like in nuclear physics. Just sum the mass of the constituents. They're all in the lowest state, essentially an S wave for the low-lying system, like the proton and the neutron. And the total angular momentum of the system is just the sum of the spin of the constituents. And this picture works very well if you just restrict yourself to spectroscopy of hadrons. But now if you do more detailed experiments, essentially you want to really determine what is the spatial distribution of those degrees of freedom, then you do high energy scattering experiments, then you get a completely different picture. In the modern picture, I would say, all the fundamental degrees of freedom are not just the massive constituent quarks, they are actually almost massless point-like quarks, just like electrons, if you wish, that interacts very strongly by exchange of a particle that we call gluon. So it's a kind of a photon, but for the strong nuclear interaction. And the system is very complicated. It's not just made of 3 quarks, but you have lots of quark, anti-quark pairs. You have lots of gluons that exchange. And all those particles are not in a pure S wave. It's really a very small system with a lot of energy. So we have a lot of relativistic effects. And in particular, you have a lot of orbital angular momentum. So in our community in hadronic physics, we really try to understand how much of the mass or the spin of the system comes from the different constituents and their motion and the dynamics of the system. And this is basically the current situation. You see that we still have large error bars on the estimation of different contribution. For example, for the total mass, you have a contribution from the quark kinetic energy. You have a contribution from the quark mass, essentially it comes from the Higgs mechanism, you've probably heard about. And then basically the gluon contribution to the mass of the nucleon is basically unknown. And there's a really a line of research in that direction, especially also in connection with new machines that are being built, for example, in the US, called the electron-ion collider, that should provide us new clues about these contributions. And also there's been a long story about the decomposition of the spin of the nucleon in terms of quark spin contribution, gluon spin contribution. You see it's very large, but so far we cannot really say what's the uncertainties. It can be as large as the value itself. So really need further experiments, and the orbital part, we basically don't know much experimentally about it. So it's really a complicated system, and the more observables we have, the better we can constrain and understand the inner structure. So one way to do this is to probe the spatial distribution of charge. So how can we do that? Essentially, you do elastic scattering. And this, most of you are probably familiar with. For example, if you do crystallography, you can do, for example, X-ray diffraction. Just if you want to know what is the crystalline structure, you shine X-rays on the crystal, and then each ion will scatter the plane wave. And depending on the position of the ion, you will have a difference in the path that will be followed by the plane wave. So we will have at the end for the observer an interference between the different scattered waves, which end up into a diffraction pattern like this. So this one is simulated, but the experimental one are close to that one. And typically to reveal such a structure, you need that the typical scale of the probing system. So essentially here would be the wavelength of your initial X-rays should be in the range of the order, if you wish, of the distance between the two ions in the system. So typically, that's given by the condition here. So the diffraction pattern gives you directly information about the square of the scattered amplitude. And quantum mechanically, probably have seen that essentially, the scattered amplitude is essentially a Fourier transform of the charge distribution. Oops. So each center will be the source of a spherical wave, and very far away from the scattering center, you can approximate the spherical wave by a plane wave, and they all interfere to get the final diffraction pattern. That's basically what this equation says. So the message here is that you measure essentially the diffraction pattern, you get information about the scattering wave, and from the scattering wave, you can infer something that we call the form factors, which contains all the information we are looking for about the spatial distribution of charge. And they are related by just a Fourier transform. So that's basically the idea over here. So this is for a crystal. So if you work with crystal of atoms, they are typically, the typical distance is about around the angstrom, which means that you need energy of the order of 10 kilo electrovolts, so which is really in the range of X-rays. But now if you want to use the same idea or the similar techniques to study the spatial distribution of charge for nuclei or even nucleons, well, it's a completely different scale because you are at least 5 orders of magnitude smaller system, which means you need 5 orders of magnitude higher energy, and you cannot easily produce and control electromagnetic waves with such energy. So that's why people, instead of doing scattering with X-rays or magnetic wave, they use scattering with electron beams. It's very easy to accelerate electrons and reach such high energies. So basically the theory, I won't go into the details, but just to give you the setup, is the following. So we will, most of the time, people will consider that we can neglect the recoil of the targets. We have a kind of infinitely massive target, and then we shoot electrons on the target. So that's what is represented here. We have electron that hits a target. The target doesn't recoil, and the electron bounce because of Coulombic interaction and all that into a final state with momentum pf at a certain angle with respect to pi. And you can define, conveniently, you can describe everything in terms of the momentum transfer, which is a difference between the initial and final momentum, which you can relate to the wave vector over here. So we are, if we consider elastic scattering, for elastic scattering, we mean that the energy of the initial beam is the same as the energy of the final beam. It means also that the momentum of the initial electron in modulus is the same as the momentum of the electron in the final state. And so basically the differential cross-section, so the probability to scatter the electron in a certain direction is given by the square of an amplitude from the initial state to the final state and depends essentially on the scattering angle. We have that. The usual thing is to consider the Bohm approximation. So if the interaction with the target is small enough, we can approximate the scattering of the incoming wave, or the plane wave that will describe plane wave electrons, as a single scattering. And if you do so, well, basically the amplitude would be kind of a Fourier transform of the potential. That's what symmetries of space-time tells you. And if you look at the particular case of a Coulomb potential that you will write just as the sum over all the charges, the point charges, and you distribute it with a distribution rho, you integrate over all the positions of the point charges, you get the total Coulomb potential. And in doing so, you can write your scattering amplitude essentially as the scattering amplitude for point-like objects convoluted or multiplied in this case by an object that we also call the form factor, which is nothing else than the Fourier transform of rho. So it's exactly similar, let's say, structure as in the case with the X-ray diffraction. You measure the scattered electron, and by a Fourier transform, you can get information about the charge distribution you have over here, with certain restriction that you assume that you have only single scattering here. There's also one point that we have to be careful, is that this is fine as long as you can neglect recoil. So we have assumed, remember, that the target was infinitely massive, you have no recoil. But if you want to do such an experiment on a very light nuclei, and for example, even on a proton, well, the proton has a mass of the order of 1 giga electron volt, which is about the same energy you need to do the diffraction. So which means that you cannot neglect the recoil here. So you cannot use this non-relativistic setup that you are used to. So that's why we are forced to use a relativistic approach. So again, I won't go into the details because I know not everybody is very familiar with that. It's just to show you the generic spirit. So the relativistic treatment is the following. So we consider the initial electron. We have an initial, let's say, for example, a nucleus, a light nucleus, or it could be a proton. So the electron has for momentum pi, and the nucleon is for momentum p. What do I mean by for momentum? So in relativity, we are taught that we can combine the 3 momentum of the particle and the energy of the particle into a 4-component object, kind of 4-component vector. That's what we call a 4-vector. And when you move from one frame to another, relativity tells you how to combine, or how the energy and the momentum measured in a frame are transformed into the energy and momentum transformed in another frame. So in general, we should respect conservation of energy and momentum. You have a symmetry of the physics under translation in space and time. So this implies that total energy of the system should be conserved, total momentum of the system should be conserved. So written in terms of form momentum, it just means form momentum conservation. So if you add the initial form momentum of the electron with that of the proton or the target, it should be the same as the sum of the final electron and the final state nucleon here. And when we talk about elastic scattering in the relativistic context, we do not necessarily specify a frame where the energy of the initial state is the same as the energy of the final state's electron. We can always find a frame that does the job. But what we mean here is that in the scattering, since there is some energy and momentum that is transferred between the electron and the target here, so the proton that is flying like this, we are considering the cases where there is no excitation of the system. So it means that what we call the dispersion relation, so how energy and momentum are related, is essentially given in relativity by the mass of the particle. So if you know the mass and the momentum, you know automatically the energy for a free particle. And so since the state is not excited, it has the same mass for the initial state and the final state. For the electron, it's a bit trivial because so far as we know, the electron has no fundamental inner structure, so it has necessarily the same mass before and after. So that's what we mean by a relativistic elastic scattering. And that's where I skip the details, but you can do exactly the same thing as before. You can write the total differential cross-section essentially as the differential cross-section for point-like objects. It would be just a point over here. I didn't mention the wavy line here represents the electromagnetic interaction. So it's just the electron interacts electromagnetically with the proton over here. So for spin zero targets, the ratio between the total cross-section and what you would expect for point-like targets is given by a function that is a Lorentz invariant function. It's the same for any frame. So it's very nice because we are not required to go to a certain frame to have that object. We can do it in any frame and you get always the same quantity. And for spin zero target, which is the simplest target, it's just one function. And if you increase the spin of the target, you have more than one function that appear because your target has spin and you have additional form factors associated with spin. So typically for spin 1/2, that's a very important and interesting result. You have two form factors. One is called the electric form factor and the other one is called the magnetic form factor. We'll see why we call them electric and magnetic a little bit later. Okay, so that's basically the idea. You do the scattering, you look at how the electron is scattered, making sure that the proton is not excited, and then you can extract from experiments functions in here. And so what we want to know is whether in a relativistic context, taking the Fourier transforms of these guys, or maybe a combination thereof, can be somehow interpreted as a spatial distribution of charge. So to do so, before doing so, let's have a look at how those form factors for a proton and a neutron look like. So in black, you have essentially a compilation of experimental data. And with you see that you have very precise data because this is the two horizontal lines gives you the uncertainty. And then in red, you have the latest state-of-the-art lattice calculation. So it's essentially simulation, ab initio simulation on the computer of the fundamental theory that describes the interaction between quarks and gluons, so the constituent of the nucleon. So there's been a lot of improvement on the lattice side, but as you see, the description is not yet perfect in all the cases. And this has to do with the fact that in order to be able to do such a calculation, we have to people have to compute things in a finite box. So you cannot consider infinite space-time, but you have to consider a hypercube of finite size. Not too large because this is very costly, but not too small because you need enough space for the system to be correctly described. And then The other problem also is that you have to make sure that what you describe, what you measure or you compute on the computer really corresponds to the ground state, so the nucleon, that you do not excite it. And also you have to make sure that you can select nucleons with a given momentum. So there's still work to be done, but at least, okay, I haven't here the progress with respect to the old situation, but things are pretty good. So especially for the neutron, for the magnetic case, things looks much nicer. And also for the neutron, you see that in the neutron case, the experimental value for the neutron electromagnetic form factors are not so nice. And this has to do with the fact that we do not have a free neutron target. We do have free proton target, but not free neutron target. So we have always to consider, for example, a bound neutron, for example, in helium or deuterium and so on, correct for nuclear effects, and say that the rest is due to the internal structure of the neutron. And this explains why we have larger uncertainties. So lattice predicts something that is rather smooth. Maybe experiments maybe suggest something more exotic, but we definitely need more data. So that's why many experiments try to get more and more data. In particular, it's important to get value of the extraction of the electromagnetic form factors at very low momentum transfer, very small kick, which is very hard to do experimentally, because that's where the largest uncertainty lie. Also on the theory side, that's also the one that is most interesting. So just to give you an idea of how those form factors look like. So how do we interpret them? So historically, in the 60s, Sachs proposed to interpret this object in the so-called Breit frame. This is so-called the brick wall frame. So the idea is that you go in a frame where the initial proton goes in certain direction with momentum p. It interacts with the external electromagnetic field generated by the electron, and then bounces back with exactly the same value for the modulus of the momentum, but in the opposite direction. It's convenient to define two objects. Essentially, one is the average momentum between the initial and the final form momentum, and the form momentum transfer, as usual. So working in the Breit frame means that the average P has to be 0. And the fact that energy and momentum are related impose that the energy transfer, which is over here, the energy transfer to the system can be written in terms of this combination of the three momentum, the average 3 momentum and the 3 momentum transfer. And since P is equal to 0, it already means that in the Breit frame, you have no energy that is transferred to the system. This is really nice. It's really working in the center of mass of the electron nucleon system. So if you have no energy that is transferred to the system, you're not exciting it, you are indeed doing an actual elastic scattering, and that's probably the best way to give an interpretation in terms of charge distribution. So if you look at the lower part of the diagram where you're at the interaction of the electromagnetic field with the nucleon, with the initial state and the final state over here, we can look at the matrix element of the operator that connects the nucleon with the external electromagnetic field. That operator is nothing else than the charge operator. So you have the charge density operator that we call J0. This is also part of a 4-vector, but okay, this is the charge density operator, and this is the charge current operator. So if you look at these matrix elements in the Breit frame for spin 1/2 target, what you get, what was the nice result of Sachs, is that this amplitude that you would naturally associate with the density of electric charge is solely described by the GE form factor. So remember, that's the one that enter here in the cross section. So it's very compelling, and the one associated with the current or the flow of charge is given by the other one, and that one is spin dependent. Is given by GM, essentially non-relativistically, you can think of the magnetic dipole moment of the electron as due to a small current of electric charge around the center of the axis of the nucleon. That's basically described by the second form factor, GM, that we called magnetic form factors. So this really motivates considering the Fourier transform of those form factors. So for example, if you take the first one, you take the Fourier three-dimensional Fourier transform, you get an object that can be interpreted in some sense as a spatial density of charge distribution, but now in the relativistic context. Something that is usually not so much discussed is that actually there's an ambiguity, because we have to normalize these quantities, and depending whether you normalize with 2 times the mass or 2 times the energy in the Breit frame, you may have extra factors that appear here, which I wrote in blue. So traditionally, people use just the black expression, but others, like in Frier and Nägele, they advocated that the correct thing to do would be with the blue thing. Well, there's been dispute for many years about which one should use, and this came with the problem that in this picture, we do not have a nucleon at rest. You see, a nucleon moves to the left and then moves to the right. So the nucleon is always moving. So relativistically, we think that the charge distribution must be somehow Lorentz contracted. And so what you are measuring is not the rest frame charge distribution, but a charge distribution in the boosted frame. And so people usually think that you have to correct for that, and so somehow implement a boost from the Breit frame to the so-called rest frame of the system. And this is really complicated. It's really relativistic and dynamical, and nobody can do it in a Lorentz, let's say, in a model independent way. And so you can see this as a kind of convenient definition which may receive relativistic corrections. And since these relativistic corrections were not clear at that time, history just kept the simplest expression, which means the one without the blue. So for about 40 years, that was basically what people were doing. They were measuring the electric and magnetic form factors, doing a 3-dimensional Fourier transform to see what you get. To give you an idea what you get with the current extraction of the form factors, let's say for the proton, that's what you get in position space. So the charge distribution associated with the form factors I showed you before are given here. So in black, so first in red is the one that's usually people use without the 1 over square root of 1 plus tau factor, just relativistic factor if you wish. And then in black, that's the one that includes a relativistic factor. So you see that relativity may make a strong difference in how the charge distribution may look like. Another hint that relativity is very important for the structure of nucleons is when you compare the proton charge distribution, even here, with the nuclei charge distribution. So for very heavy nuclei like samarium, nickel, lead, the structure is the following. You have essentially a flat constant charge density. It's a bulk constant density. And then for certain width, certain distance from the center of the nucleus, you have a transition from the flat plateau to 0. And this is called the skin of the nucleon. And as you go to lower or smaller and lighter nuclei, you see that the shape becomes way different. And the proton, in some sense, is the one that's the asymptotic or the most distorted one. In a sense that for nuclei, you can somehow define 2 regions, which is the inner, where you have constant density, and then the skin. While for the proton, you have no distinction. So it's as if the proton is only skin. It's a skinny proton, if you wish. So it's really a relativistic effect that you have this kind of structure and not something like this. If you do this for the neutron, well, this is a picture you get. So we know that the neutron has total charge equal to 0, but the charge density is not 0, which means that in some places the charge can be the charge density is positive, and in other places it's negative. So it turns out that the center of the neutron charge density is essentially positive, and then you have the exterior or the far region is mostly negative, and the integral over this and over all the angles give you 0 because you have total charge equal to 0. Again, here the two curves really show the effect of a relativistic correction factor, typical relativistic correction factor you may have. So can we understand why the center should be positive and the outer region could be negative? Well, there's a simple picture that really easily accounts for that. And this is based on the idea that the neutron somehow quantum mechanically can fluctuate into a proton-pion state. The nucleon is heavier than the pion, and that means that the pion essentially orbits further away from the center of the system than the proton. The proton being positively charged, it is responsible for the positive inner core, while the pion that is negatively charged is responsible for what we call the pion cloud. Questions?
No, I don't see any yet.
No? Okay.
Yes, actually, I could not raise my hand. Sorry.
Oh,
So I have a question here. So Cédric, so these plots that you were showing, they are using the form factor from experimental data or a model?
Yeah. So those are from fits the fits to experimental data. So regularly, they are fits that are done by several collaborations using the world's data, and then you can use them to do prediction and calculations.
Okay, thank you.
It's really based on experiments. It's not a model.
Okay.
Okay. Okay. So this is, let's say that this time.
We indeed have a question, Cédric. Sorry to disturb.
Yeah, sure.
Shumiran, go ahead.
Excuse me. So I'm not from the field, but I was curious about your comment about you cannot boost back or go back from this Breit frame to the rest frame. Like as an undergraduate, I would think I could just do some inverse Lorentz transformation and do it. No?
Well, yeah. So if you're working with a system of free particles, you know how free particles are transformed from one frame to another. But once you include interactions, you cannot do it unless you manage to solve the theory. And it turns out that the theory that describes the system of quarks and gluons is so complicated, it's nonlinear and so on, that we do not have exact solution to this system. So we cannot do it in a model-independent way.
I see. So you are saying that if you implement it, the answer depends on which model you are working with.
Exactly. So there are different people that use a different simplified version of the theory. They use different models. And so they end up with factors like this with different powers. So this is really a typical Lorentz correction factor with different powers. And depending on the model and how you implement effectively the boost transformation with the interaction, you get different factors.
I see. Okay, thank you.
Welcome. Other question?
No, not something I see.
Okay, so for about 40 years, that was basically the only thing that we can do. So basically, this picture is exact in the non-relativistic limit because tau is just divided by the energy of the system, which is much larger than the momentum transfer. So if you can neglect the recoil, everything is fine. It's non-relativistic. But as soon as you have recoil, like for the proton and so on, these kind of factors are very important, which are shown in here. So beginning of 2000, so about 20 years ago, a new picture emerged, which is essentially the one based on the infinite momentum frame. So the idea is that instead of working in the Breit frame, where the initial and final momenta are just opposite to each other, so just the proton just bounce symmetrically and elastically on the electromagnetic field. here we are considering a proton that is moving so fast that the interaction with the electromagnetic field almost doesn't change appreciably the momentum of the system, and then its energy. So if the momentum, let's say in the z direction of the nucleon, is so large, and then you do scattering on it, well, basically the change in energy and the change in momentum in the, let's say, in the z direction are much smaller than the average energy of the system. And so you are not really disturbing it. Or if you wish, since the energy represents essentially, gives you essentially the inertia of the system, if you have a system that is moving super fast, the inertia of the system is very large. And if it's very large, it's essentially behaving as if it was a non-relativistic system, because for non-relativistic system, the inertia is much larger than the actual velocity or kinetic energy of the particle. So in that case, you can repeat exactly the same thing. So you look at the matrix elements of the charge density in this infinite momentum frame. And what you observe is that, okay, matrix elements are a little bit different. You have now two functions instead of one. Remember, in the Breit frame, you had only one function, and which was spin independent. While now on the light front, you get two, or the infinite momentum frame, you get two contributions, so F1 and F2, which are linear combination of G and GM we had before. They are called Dirac and Pauli form factors for those who have already heard about them. So we have two of them, and one again comes with no spin dependence, and the other one comes with a spin dependence. And this then motivates to take not a three-dimensional Fourier transform, but the two-dimensional Fourier transform, because you neglect delta z in front of pz. You don't have sensitivity to delta z, so momentum transfer in the longitudinal direction. If you wish, the physical picture is that under a Lorentz transformation, you change the velocity of your system. The system appears to be what we call Lorentz contracted. If you make a measurement of the longitudinal length of your system, it gets smaller and smaller. It shrinks in the longitudinal direction if you increase the velocity of the system towards the speed of light. And so in the limit where you have infinite momentum, you're almost looking at a proton which is moving with the speed of light. So it means that your proton looks like essentially like a pancake. So you have lost information about the longitudinal dimension, but not the transverse direction.
One question, please.
Yes.
Here you are using lambda prime lambda to show the spin dependence.
Yes.
I mean, you are using a different symbol here just because it's a different Lorentz frame. That's all.
Exactly. So that would be an important point, and we come back later.
Okay.
So I will come back to that point. So in the Breit frame, I will call it S. Yeah. In another frame, polarization, I will call it lambda. I will explain how those are connected. But it's a very important point. It's a very good point.
But both are spin projections of the proton.
Yes. So both are spin projection along a certain direction, and you define them in a certain frame.
Right. Okay. Thank you.
But I will explain this a little bit later. But this is a very important point, indeed. Yeah. So we have two contributions. And since the nucleon looks like a pancake, well, you have only the information that you get is essential. And so this is what you get. So you get a two-dimensional Fourier transform. So you have a term. So if you take, for example, so you have a term that is associated with the spin-independent contribution. Doesn't depend on the polarization, the value of lambda, essentially given by F1. And then you have the other term that is driven by the form factor F2 that we usually associate with the anomalous magnetic moment. But okay, this is just a detail. The nice thing about the light front, since I mentioned, is that the inertia of the system is so large that you do not have recoil correction anymore. You don't have to worry about recoil correction. It means that these Fourier transforms are exact, and you don't have to correct for additional relativistic effects. And you can even think in terms of square of wave function. You can really think of F1 and F2 as written in terms of square of a wave function, but not the wave function of a proton at rest, but the proton moving with the infinite momentum, which means moving with the speed of light. So this is very interesting to have no recoil correction compared to the Breit frame. And that's why for about 20 years, some people were pushing, saying that, okay, maybe we shouldn't use the Breit frame, but we should use the infinite momentum frame. And then instead of using the GE to describe the charge distribution of unpolarized target, we should use F1. So if you look what you get with these two-dimensional densities, well, for the proton and when you polarize, for example, longitudinally, you get something that is, well, it's axially symmetric, nothing very exciting, just about half a Fermi radius, just as what you expect for a proton. So everything is fine. Now, if you do the same thing for the neutron, here comes the surprise. Surprise in 2007 was advertised by Jerry Miller, is that if you do this two-dimensional Fourier transform with the form factors for the neutron, you observe that instead of having a positive core and a negative tail, you get a negative core followed by a ring of positive value and then another outer ring of negative value. And it's very surprising because we don't have any simple idea. We had actually no simple idea of why when the neutron is moving with the speed of light, the charge distribution looks negative in the middle. So there has been a couple of papers of Jerry Miller and collaborators trying to understand that from a dynamical perspective, working with models and so on, but they never reach convincing arguments. The other thing that is also interesting is that for these 2D charge distribution in the infinite momentum frame, well, if you polarize the system in the transverse direction, so you have to think that these are the picture when the proton is moving towards you with the speed of light. So if you look at the polarization in the transverse direction, so it being that direction, the x direction, well, the charge distribution is not axially symmetric anymore. You have the contribution from the F2 form factors that now contributes and shifts the distribution sideways. And so if you have a shift, it means that you have a contribution from an electric dipole moment. So for example, for the neutrons, the total charge is 0, the dipole structure appears more clearly. And this is what you get. And so it's a bit surprising because electric dipole moment, what does it mean? Because of parity, time reverted symmetries, which should be respected by the strong force in the electromagnetic force, should prevent the existence of electric dipole moment. And while we see clear electric dipole moment. Well, this has been understood, the last effect has been understood very quickly as follows. So remember that the picture I show were not the picture of the nucleon at rest, but the nucleon moving with the speed of light. Equivalently, we can say, okay, we can set the nucleon at rest, but it's the observer that is moving with the speed of light. Essentially, it's just like if you were sitting on the photon that is interacting with the system. And relativity tells you that the charge density in a certain frame is a linear combination of the charge density in another frame and the current in that other frame. So for example, if you're looking at the charge density in the infinite momentum frame, it's not just the density in the rest frame, but it's a combination of the rest frame density and the rest frame current in the the z direction. And this is really what relativity tells us. So if you apply this to our system, so here it's not our neutron, 1 u quark, 2 d quarks, it's positively charged u quark, negatively charged d quark, and you look at the system that is polarized in the x direction. So that would be in the going inside the plane. So if the spin going inside the plane, and then we look at the magnetic moment of the neutron, the magnetic moment of the neutron is negative. So to get a negative moment for that, you need the up quark to orbit. Well, they have a higher chance to orbit like this, so anti-clockwise, while the negatively charged particle, like the d quark, have a higher probability to orbit clockwise. So if this is the rest frame charge density, while you have a rest frame charge density, you can also infer the sign of the rest frame charge current. So on the upper side is essentially negative, so the z direction is towards the right, while here the current is positive. So the charge current is going that way, and the charge current that side is going that way. So it's positive here, negative here. And so when you sum the rest frame density and the rest frame current, this explains how you have a depletion of charge on the upper side and an increase of the charge on the lower side. So it's really a relativistic effect of how the charge density is transformed one frame to another. And so there is nothing wrong with having electric dipole moments. Okay, I'm already running short of time. Of an electric dipole moment, it doesn't violate any fundamental symmetry of parity in time reversal. It's just an induced effect due to the fact that you're not looking at the density at rest, but the density in a moving frame. The other aspect that is important to take into account is that this explains the dipole here, but it's not sufficient to explain why we have a negative center here. While the other piece that enters the game here is another very unintuitive effect, relativistic effect, is that boosts do not commute. If you boost in the x direction and then in the y direction, you do not get the same thing as boosting first in the y direction and then in the x direction. This is purely a relativistic effect. And this implies that polarization, the notion of polarization, and many other things like position and so on are frame dependent. So consider that you have a system which is at rest, let's say the state is at rest, with certain polarization would be projection of spin, let's say in the z direction, the ordinary spin. And then what do we mean by polarization in other frame? What we mean is essentially that you boost the frame with, for example, a rotationless boost. That would be canonical spin. So if you boost to any frame, well, the polarization we call S in that frame, it has just the same value as the rest frame polarization. If you go to the infinite momentum frame, well, still the canonical polarization, but in the infinite momentum frame. So far, so good. But where things become really tricky and makes things hard to really picture is that if you take a boost from the Breit frame to the infinite momentum frame directly, what you obtain is not this state, but you get a state that is rotated in polarization space, which means you take with a spin up in the Breit frame, you boost directly to the infinite momentum frame without going first to the rest frame. Well, you get a state which is not infinite momentum frame with spin up, but would be a linear combination of spin up and spin down. And this is really a relativistic effect that we call a Melosh-Wigner rotation. We have to accept it. That's we don't have much intuition about it, but that's something that has to be taken into account. And this explains why, when you work in the Breit frame, the spin-independent contribution was given by essentially the form factor GE, the electric form factor, the spin-dependent one by GM. But when you go to the infinite momentum frame, this rotation mixes spin-independent contribution. And then that's why in the infinite momentum frame, you have F1, which is a linear combination of G and GM given here. And the specific factors here are essentially information that you get from this Wigner rotation. So one question that we may ask, is there a set that is more physical than the other? And so that's where I come in and propose the following. So in order to understand how the Breit frame and infinite momentum frame are connected, it would be nice to have a description that allows you to interpolate between those two situations. And the initial goal we have in mind is we want to somehow picture the spatial distribution of a system, and the system should be somehow localized somewhere and has also a given momentum. So naturally, you are led to think not only in position space or momentum space, but to work in phase space. And if you work in phase space, maybe some of you have already heard about the Wigner distributions. So you never measure directly the wave function, the wave packet of something. It's always the wave packet of the initial state and the wave packet of the final state. And so you can represent, instead of working with wave function and the wave function of wave packet and the final wave packet, you can always consider the combination of these two. Any observable will be always combined with this and do a certain Fourier transform. So the variables of this object that we call phase space density is the average momentum recover capital P, and R in some sense is the average position that you see over here. So you have the average position and you have, after Fourier transform, the average momentum P. So these objects describes, just like the wave function, it says the same information, the system, the whole system. The nice thing about it is that if you integrate this phase space density over the position, you get a pure density, an actual density in momentum space, and vice versa. If you integrate over momentum, you get a pure density in position space. And the very nice thing is that if you take the expectation value, so the average value in any state, you can really write, like in statistical mechanics, the expectation value of an operator, just the integral of all phase space of a phase space density, which describes how the system is localized in phase space, times a matrix element, which essentially represents the internal quantity of for a system, which we can interpret as localized at the same time in position and space. So of course, you know the Heisenberg uncertainty relation in quantum mechanics. So this cannot be thought in a strictly probabilistic interpretation. You cannot say that this is the strict probability that a proton is seen somewhere with a certain momentum. But it is the best compromise you can do, which involves both momentum and position. And so we call it a quasi-probabilistic interpretation. That's the closest classical thing you can do for describing the quantum mechanically the concept of a system which is localized somewhere with a given average momentum. And if you buy this, then you realize that what we call the Breit frame, which is capital P equal to 0, is actually the rest frame of a localized system. You cannot have the rest frame of the system if you want to have P exactly 0 for initial and final state. You have no information about where the system is. If you want to have information of both, having the system which is somewhere and basically at rest, the best compromise is given by the Breit frame. So in this sense, the old result in the Breit frame, you do not need to correct them for boosting back to the rest frame, because it is already the rest frame, but now of a localized system from the point of view of phase space. And so you can define a density for any momentum. And that's what we call the elastic frame. So basically, we choose the axis such that the momentum, let's say, is in the z direction, so it doesn't restrict anything. And then you can relate the energy transfer to the momentum transfer and the average momentum and the average energy. Since we want an elastic scattering, we do not want any energy to be given to the system. We need that the momentum transfer to the system in the z direction should be 0 from this relation. And since the momentum transfer in the longitudinal direction is Fourier conjugate to the longitudinal position, setting delta z equal to 0, Fourier transform means that you have to integrate over the longitudinal position. So I just have to give up something. I cannot localize my system in the longitudinal direction, but I can localize things and define density in the transverse plane for any PZ. So we can define the elastic 2D charge distribution in any frame. It would be two-dimensional, and it will depend on what is the momentum, or if you wish, the velocity of your system. And this is a very simple but very convenient expression, because it really interpolates between the two frames that I mentioned. If you take PZ equal to 0, you essentially have the Breit frame density integrated over the longitudinal position. If you take PZ going to infinity, you simply recover the infinite momentum frame distribution. So now we have a new variable, PZ, which really helps you to interpolate between the two. So this brings to the last slides I wanted to show. So if you repeat this with using the experimental form factors and this kind of formula, which I don't detail here, that's what you get. You start from the Breit frame, which is the black curve, and you increase the momentum of your proton, and you look at the charge distribution you see. That the density at the center of the proton becomes more and more positive. It's almost doubles, but it also shrinks in the radial direction, because the total charge should be the same. So how this happens from when we move the frame? Well, the reason is because you have two contributions. You have the rest frame charge density, which is the convection contribution, so the one associated with GE. And that one, when you change the momentum, doesn't change much. This is just a small effect of the rotation I mentioned before. But the main reason why the density changes is because relativity mixes charge density with the charge current. And charge current is, in the rest frame, is driven by the magnetization contribution. And so when you increase PZ, the contribution from the magnetization contribution becomes very, very large, because also the magnetic moment of the proton is a large number. And when you sum this with this, you get a large increase here. And this similar analysis explains why the center of the neutron in the infinite momentum frame appears to be negative. For the neutron, we start again with the Breit frame over here. We increase the momentum, and then we get a negative value for the center you see here, and then a positive ring here, and then eventually it becomes negative here. So if you decompose again into convection and magnetization contribution, again, you see that the convection contribution, so the rest frame density, is always the one we know. It doesn't change much because of the associated with the Wigner rotation. It's just positive in the center, negative in the outer region. But the relativistic effect is to combine or to somehow mix the rest frame charge density with a rest frame magnetization contribution multiplied by some factor that depend on the velocity. And for the neutron, the magnetization contribution is negative. And so it competes with the rest frame charge distribution, and is larger actually than the rest frame charge distribution. And that's why reaching a certain velocity, so in this case for the momentum of 1.31, just based on experiments, you can turn a center that is positive in the rest frame, which apparently becomes negative in a moving frame. So it's really a relativistic effect which explains this. There's no dynamics behind, just pure perspective. If you really apply all the correct transformation from the rest frame to a boosted frame. So this solves the mystery we had before, and really shows that you do not really have one that is more fundamental than the other. I personally prefer the distribution in the Breit frame, but distribution in the infinite momentum frame have also their own virtue. But you have to keep in mind that there are lots of induced effects just by the fact that the proton is seen not in the rest frame, but in a moving frame. So this brings me to the summary. So really the message I would like to convey, things that we already know, but here we have more precise description of what this means, that the relativistic charge distribution are necessarily frame dependent. Unlike the non-relativistic, the relativistic charge distribution depend on the momentum of the system. And what is usually called the Breit frame of the system can really be thought of as the rest frame of a system. If you think of the system has to be also localized in position space. And in that case, you have to have a compromise between position and momentum, and the Breit frame gives you the best compromise for having a localized system around the origin with average momentum equal to 0. And then you can define charge distribution in any frame, and then you have a natural interpolation between the Breit frame and the infinite momentum frame. And all the weird things that appeared in the infinite momentum pictures have nothing to do with the dynamics. It's only artifacts coming due to relativistic effects, which mix rest frame charge density with rest frame current density, and also create rotation of spin. All the rest, all the difference in rest frame and infinite momentum frame densities are just associated with those effects. So that's all, and I'm open for questions.
Thank you very much, Cédric, for this nice overview talk. So we have some questions, but maybe we have a few more. Yeah, go ahead. Ashmita, do you want to ask a question?
Yeah, so
yeah,
that was a very interesting talk, and I also saw your paper. I found it very interesting. So this infinite momentum frame charge distribution in the infinite momentum frame, this two-dimensional charge distribution. So basically here the boost is this Galilean boost, right? That is why I'm saying it is not a dynamic.
Okay, so once you have reached the infinite momentum frame, you have still the possibility to boost the system, let's say in the with a little bit in the z direction or in the z or x and y direction. But these little boosts are so small compared to the very large momentum of the system. In that case, those densities are not very sensitive to the small deviation from the large PZ. So you can have large PZ with a little bit of delta PZ or delta PX or PY. It doesn't change the picture.
Okay, so this boost, the Galilean boost, it does not involve dynamics, and that is what you have said. The difference in the two prescription comes purely because of the mixing of contributions from this convection thing and the magnetization thing.
Exactly. So you have this. So the rest frame density is GE. This one is given by GM. So the density combines the two. So you have the density in the infinite momentum frame involves GE and GM. And the other effects is that for the Breit frame, GE is unpolarized, GM is polarized. If you mix the two, you would say, okay, I look at the unpolarized distribution in the infinite momentum frame, I should just have GE. But because of this spin rotation, the Wigner rotation, GM will also develop a spin-independent contribution, which will combine with GE to form what we know as F1.
So you have considered only longitudinal polarization, right? Spin.
So, yeah. So okay. So
direction. Yeah. Here you have considered transverse polarization. Do any of your other plots show transverse polarization?
So you can do exactly the same. Okay. So in the plots I showed at the end, it's indeed for the unpolarized or the unpolarized or polarized in the z direction. That's the same. If you put it with the polarization in the x direction, I should have made things which are two-dimensional to see this transverse shift. But if I keep, if I can then extract, I haven't done explicitly, but you can do it, proceed exactly the same way and see how from GM you would evolve into something that look like F2. Sorry. How from you start from GM and going to the infinite momentum frame. This is this combination that comes from, and we will have all the intermediate expression from GM to F2, which are given in the paper. You just need to do the Fourier transform. So it just shows how something which has no dipole involves a dipole shift that will increase with PZ.
Okay.
Okay, just hello. I'm Urjit here. That was a very nice talk. Really very interesting. So does this raise our hopes about the gluon contribution to proton spin?
Okay, so the ideas which are already here basically developed for the charge distribution, it applies to any spatial distribution. So for example, if you are interested in the gluons, you can extract from other experiments like deeply virtual Compton scattering information about what we call the generalized pattern distribution of the gluon. So basically they give you the combined information about the longitudinal momentum fraction of the gluons and the position of the gluons. In that context, people usually work in the infinite momentum frame because that's also in that setup that you do the experiments. You see the nucleon is you hit the proton with the probe with very high energy, high momentum. So from the point of view of the target of the projectile, you see the proton as if it was moving with almost the speed of light. So in that context, high energy experiments, it's natural to think in terms of the infinite momentum frame distributions. But if you look at these gluon distributions, so other quark distribution, you will have lots of distortions like that one. When you look at momentum space, it's not only the charge, but other quantities, momentum, spin, etc. And they do not necessarily look very natural, except that. If you want to connect with the picture that we are more familiar with, this rest frame picture, you will need to be able to connect these with the Breit frame picture that people don't use usually. So we can use basically the same idea of elastic frame to interpolate between this infinite momentum dimensional frame with Breit frame, where you have a more idea of effective motion of particles in the rest frame. So really thinking in terms of the light front is nice for several mathematical properties like density interpretation, Galilean symmetry, but at the same time you have relativistic artifacts that mixes different components because you always think the red frame is more natural in our case.
Okay, thank you.
Any other questions or comments? No, I don't see any immediate questions, Cédric. So let me thank you again for this nice, interesting talk. And also I thank all the participants for joining in this
Thanks, Cédric.
seminar.
Thank you.
Thank you. Very nice talk.
Thank you.